I would like to introduce you. We are delighted to have this talk by Krystyna Kuperberg, who did that remarkable work of a C-infinity counterexample to the Seifert conjecture. And today she's going to talk to us about shape theory meets dynamics. Welcome, Krystyna.
Thank you very much. Thank you very much for inviting me, and happy birthday to Paul. I hope he can hear it. He is there.
Yes, I can.
Okay, great. Well, happy birthday. I actually put it on the board behind me, but the light was bad. So I met Paul several times, and in Europe and in the United States. And just looking by my old pictures, through some old pictures, I found some pictures from a topology conference in Texas, in San Antonio in 2000. And this is Paul and Sergei Novikov in that picture. So I'm going back to shape theory. I'm saying I'm going back since that's actually was my first experience with topology. So what is shape theory? It's really like Vittori's type homotopy. And it was first introduced almost by Vittori's. He defined the Vittori's homology. He proved the Vittori's mapping theorem in that paper from 1927, and also indicated that this kind of methods could be used for homotopy. And he did define the first homotopy group in that paper. And then people came back to it, and it was Christie, and he used Czech groups, and he actually proved a very, very restrictive version of Jurevich's theorem, because actually some stronger assumptions are needed there. Then some ideas came from Grothendieck, and in form of et al. Homotopy. And there is a very nice book by Arten and Maser from 1969. So that kind of approach is just look at compacta as inverse images of ANRs or polyhedra. ANRs, since infinite dimension, some are of infinite dimension. Well, Borsuk came to it in the 60s, mid-66 maybe, and first started to lecture. And as I recall, I was an undergrad student there in Warsaw. He first tried to use Vittori's approach of those little steps. That's very tedious. That's not very really good to work with. And then, but Borsuk lectured, and then Borsuk came with an idea to really embed a bed compactum in a manifold, or the Hilbert cube, or some nice ANR. And that approach not only inspired many people to work on many problems, it was very geometric, and for dynamical system, for dynamics of manifolds, that's really a very convenient approach, because you can really see what is happening. So let me just say a little bit about shape theory. You have two compacta, compact spaces, X and Y, and that's the Borsuk original definition. He used everything in the Hilbert cube. Then he extended to Hilbert space. But you basically have a map from X to images are closer and closer to Y, but the reason the domain is extended, same as range, is to have a composition, that the composition is well defined. But it's really a sequence of maps from X into neighborhoods of Y, and they are close to each other. They are homotopic in some neighborhoods. So it's really absolutely equivalent to looking at inverse limits of ANRs. But for dynamics, I feel that this approach is much more convenient. So what Borsuk did was just for metrizable spaces, metric spaces, and AR, absolute retract, ANR, absolute neighborhood retract, not necessarily compact. So something like the plane or the three-dimensional space or the Hilbert space, those are very convenient ARs to put X and Y in them. So the same definition as before, except instead of the Hilbert cube in both places, we have one AR and another AR, and fundamental sequence from X and Y is a sequence of maps from the first AR to the second one, such they are coming closer and closer to Y, and they are closer to each other in neighborhoods, closer in the sense of homotopy. So homotopies, all maps are very nicely extendable in ARs. And that mapping allows to define homotopy groups, which Borsuk called then fundamental groups. Other notions, the shape homology and cohomology are the Vietoris-Czech groups. So because it's for metric spaces and we can assume that it is locally compact, we can use Vietoris, which seems to be convenient sometimes. And two maps to such sequences are equivalent, shape equivalent, if they are just closer and closer to each other in some neighborhoods. And then there is shape equivalence defined. For one thing, if there is an actual map from X to Y, it can be extended to the whole AR, both in the domain and the range. And this shape was unique. And two fundamental sequences give shape equivalence if both compositions are shape equivalent to the identity, one in X and the other in Y. And then we can say that X and Y are of the same shape if such maps exist, or write that the shapes are equal. But there are many convenient theorems, propositions, a lot of work that was done by Borsuk in the very beginning. He did prove all those low, tedious lemmas, some difficult cases, but lots of that was just going very carefully through very specific definitions. So shape equivalence independent of the choice of the two ARs. If X is in, say, the Hilbert space and Y is in the plane, that can happen. And we have shape equivalence between these two, and then we embed them differently. X in some Rn, Y in some different Rm, then the shape equivalence is independent of those choices. It's independent of the embedding as well. If X and Y are ANRs, shape equivalence is the same as the homotopy equivalence. And shape homotopy groups, Vietoris-Czech homology, cohomology, usually Spanish cohomology, they are all invariant under shape equivalence. But some unexpected things started to happen almost immediately. The shape of planar connected compactum depends only on the number of components of the complement. So strange things happen. If it is the sine 1 over x circle has the same shape as a circle, the Sierpinski carpet has the same shape as the Hawaiian earring, because the number of complements, the number of components of the complement are the same. For example, the Menger sponge has the same shape as the Hawaiian earring. So it's a little bit not what one would expect. anything contractible will have the same shape as a point. There is a very important notion that was used and introduced by Borsuk quite early, and that something is movable. Again, we put a compact set F in a AR or ANR. This time it doesn't matter because we'll be extending some F's only locally. And F is movable if for every neighborhood there is a smaller neighborhood such that the image can be moved arbitrarily close, such that the neighborhood can be moved arbitrarily close to the set within the middle neighborhood. The thing different from dynamics here, like it will be similar to attractors, but what is different, the set F can be moved as well. It doesn't have to stay in place. This notion is independent of the ANR and is independent of the embeddings. So if something is movable in one space where it's embedded with one ANR is movable in another, it's really a shape invariant. So once a new theory is formed, like shape theory, new homotopy theory, one will want to prove just the classical theorems. And they do extend, like the Vittori's mapping theorem extends, but only for movable spaces. It's very easy to construct examples that it does not work in general. Even the Hurewicz theorem. The Hurewicz theorem works for movable spaces. And of course, some of those assumptions can be weakened, but in general, because of the homotopy groups of spheres, one could construct sort of spherical suspensions of spaces for which the Hurewicz theorem, just taken as it is, does not work. So not only if the compactum is in the plane, that it's movable, that was actually shown by Borsuk. It is, the Hawaiian earrings is clearly movable. And so one can show that anything in the plane is movable as well. But Macmillan showed that if something is embeddable in a surface, a compactum embedded in a surface, that X is movable as well. And Paul, of course, has this fantastic example of a C1 vector field on S3 without circular orbits, without compact orbits, non-singular and no circular orbits, showing that the Cipher conjecture in dimension 3 had a counterexample. The minimal sets in that constructions are the Denjoy continua. The Denjoy continua are subsets of the surface of a torus of a surface, and those are movable. So one of the first example that comes to mind that is not movable is a solenoid. This is probably the most natural example. And as one can see, in a solenoid, it was shown as an intersection of nested toroid that this green torus could not be moved close within the yellow one to something that goes around more times. And why are solenoids interesting? There is still many things not known. If it's a solenoid, there is a minimal set in a flow, the neighborhoods, the projectors in the neighborhoods can behave very strangely, and the solenoid cannot be isolated, but it's not actually clear what is happening usually in neighborhoods. And I'm talking mainly about dimension 3, because in higher dimensions, a solenoid can be isolated in a continuous flow. say like in dimension 4. So I want to say a little bit about solenoids because in a way that's what I can show a little bit more about. So solenoids is usually shown as the inverse limit of circles. Each map is a covering map. It's actually can be considered as a group, and it's homomorphic. And that would be the approach of approximated with ANRs. It could be also shown as the intersection of tori, say in the three-dimensional space, or a mapping torus of an adding machine. So an adding machine, probably, let me just put the definition just in case. It's a map, a homomorphism, defined on a Cantor set, and it's just adding. So we add one and move over to the right instead of to the left. So it's basically easier to show the example. We are used to base 10. So if we add 1, we get to 9, we get 0, 0, 0, and then the next number jumps by 1. The only additional thing is that the sequence 999 maps to 0. So it still doesn't seem to be known if there is if in case of a homeomorphism of the plane that we can say is orientation preserving, doesn't matter with an invariant adding machine, if there is a periodic orbit in every neighborhood of the adding machine. So I want to show a little bit about it. Somebody got this name cylinder, I don't know why. So cylinders would be those low Cantor sets. See here, this is actually a mapping torus, which is a solenoid. And there are adding machines as well. They're a different map, not alpha. Alpha was the adding machine of the big Cantor set, but some power of alpha. So that's the setting that I want to have, a homomorphism of the plane. We can assume it's orientation preserving because if it's not, we can just take h to the power 2 and get orientation preserving. And we have an adding machine. And this adding machine is Lyapunov stable. If the maps, the forward orbits are coming closer and closer. And if C is Lyapunov stable, it was shown by Brodsky and Stewart, then there is always a periodic orbit of H in every neighborhood of the Cantor set. If we skip the stability assumption, that's what I have. It's if there's a homeomorphism, as I said, we can assume it's orientation preserving with an invariant Cantor set on which it is an adding machine, that every neighborhood of C contains a periodic point of H, not necessarily the whole orbit, but a periodic point. Now the orbits can be large, but then coming closer and closer to the Cantor set, but in general, they can be very large. The proof is based on the idea that was used by Morton Brown, in which he proved a version, Carter-Lewis theorem. And although typos and misspellings are very common in slides, at least mine, this is really, the title is a short proof of Carter-Lewis theorem. And it's on one page, everything. The title, the abstract, the references. Carter-Lewin theorem says that if F is an orientation preserving homeomorphism with an invariant continuum X that does not separate the plane, there is a fixed point in X. In general, this is an open problem whether a non-separating plane continuum is compact and connected, that a non-separating continuum has a fixed point. It has the fixed point property. So, as again, the proof is similar to that proof, but let me just show it. Denote by P the set of all periodic points of H, including fixed points. Fixed points clearly are away from C because there is no fixed point in C. But we can include all of them. Does not really matter so much. The set P is invariant after H, under H, and so is its closure. So let's take look at the closure of P, and to saying that the periodic points are arbitrarily close to the Cantor set is just saying that the intersection between the Cantor set C and the closure of P is not empty. So suppose that it is empty. Suppose that they are really away from C. So let's cut it out. Remove the closure of P from R2. That's going to be possibly not connected, but each component will be some disk with holes. And at least one of those components would contain some cylinder, some of those little Cantor set of the Cantor set C. So, and let's take the universal cover. So universal cover of a disk with holes is a plane. And in there, there's a cylinder containing open, evenly covered disk. And it can be very, very small. And is invariant under some power of the homomorphism H. So we can take one of those disk with holes, say like this one would be disk with holes. There's a hole here and there's another one. And we have the tiny cylinder that lives to many copies. And if we compose with the appropriate deck transformation, we'll have an invariant Cantor set in the plane. That's a plane. And here we have invariant Cantor set in the plane. And no fixed points outside that. So because fixed points of the power of H would be some periodic point of H. So here we have the deck transformation. There is no periodic in the cover, which is the plane. And by Brouwer's so-called translation theorem, there has to be a fixed point, but there isn't because we cut them out. So we get an contradiction. Therefore, the closure of P has to intersect the Cantor set. Well, it's not difficult to construct a flow on a one-dimensional continuum, which in this case would be a solenoid plus some circles. So those circles get wider. So that actually on that particular set, there will be close, will be very close periodic points, but not periodic orbits. Also, in in dimension 4, one can have a flow that with a solenoid, the solenoid is isolated. And there are still some open questions as far as I know. Related to this. These are the two questions with R2 and R3. So solenoid is not movable, no matter where it's embedded, but it can be embedded in the flow as an isolated set in higher dimension. So there will be some shape theory questions specific to dimension 3, although in general, shape theory properties such as movability or other properties of that sort called UV properties do not depend on the embedding.
Krystyna, we can't see the last line of your slide, so could you read the second question, please?
You cannot see the bottom of the, I didn't realize that. Okay, so the second question is, we have a flow, an R action on R3, or just N manifold with an invariant solenoid. Does every neighborhood contain a periodic orbit? There are theorems, there are many partial results, and I'm going to mention, but result of Thomas pretty soon. Okay, maybe it would help if it was not full screen. I don't know, to see the bottom. I will try to change.
There's still the same problem, so you might go back to...
Yeah, well, I didn't get to exiting from full screen of my talk. Okay, so I didn't realize the bottom was not showing. So I'm going to go to get back to Thomas's result, but we know that solenoid is not movable. And again, by solenoid, I mean non-trivial solenoid. Some people claim a circle is a solenoid as well, so that's a disagreement. Okay, so a non-trivial solenoid is not movable, but if we look at the solenoid as the inverse limit of circles, those circles approximate the solenoid. If that's embedded in some AR, that's movable because we can project the solenoid onto those approximative circles. We get finitely many circles, and that's an ANR. So that is movable as well. So the question in shape theory is, and related to dynamics, if there's a non-trivial solenoid invariant under a non-singular flow on R3, does there exist an invariant movable set that contains that solenoid? And in general, instead of a solenoid, we can take just anything else. Would be in the flow, would it be contained in a larger set that is movable? And that's definitely related to something that could or could not be isolated. No, I don't know. Oh, something. So how can we have a solenoid in the flow that is approximated by a circle in R3? So again, a solenoid is the inverse limit of circles, but also can be the intersection of solid tori. That's here is the cross section of the tori that he will go around 5 times. And we can have a map on this, which is, say, identity on the outside, and here just some sort of action on those circles. So we can have jump from here to the next one, and next one, or skip some. Now the points in the middle will be the core of the torus. The core, that point will give you a simple closed curve. And these 5 will go a simple closed curve that goes around 5 times and possibly 2 times the other way. And next to the solenoid, we can have simple closed curves this way. But they will be knotted. They are knots, usually, very often knotted.
We still
But-
can't see. Now we can see the final last line.
Okay, so here is embedding of a solenoid and the approximate will circle 3. Okay, I'm going to try again to get out of full screen. Something happened. Okay, now it's not full screen, so you see probably a lot
No,
of.
but the
other
problem
stuff.
of full screen or not, that's not the problem. But just before you left the last slide, it was all right on full screen.
I don't know how to make it different.
The problem is here, not with you. So go ahead, please.
Okay, so I'm good. So the last line says embedding of a solenoid and the approximating circles in R3. Those circles you can see may be knotted. You could get a torus knot, but then it will be a torus knot in a torus knot, which is not a torus knot. So those knots can be pretty complicated. And it appears that at least for a stable solenoid, you can always get those tori. It appears, I don't have the exact argument, and that could be a question whether a solenoid could be approximated by simple closed curves that are not knotted, and the answer seems to be obvious, is probably not. And again, this is specific to dimension 3. So this is just an example of a solenoid that is not as isolated. It's approximated by simple closed curves that are orbits. So Thomas, in a paper that was quite old, called One-Dimensional Minimal Set, using Meyer-Vittori sequence for homology and Vittori's homology and cohomology, showed that if there is in dimension 3 a solenoid that is not isolated. So I think you can see the definition of isolated set, and everybody probably knows the definition. Is the largest is the maximum invariant set in the closure of a neighborhood, but the set is contained in the neighborhood. And using Conley theory, we can have those neighborhoods are actually very nice. And the last, what says theorem, if solenoid is invariant under some flow, then the solenoid is not isolated. And for stable solenoids, this has been shown. And here is that it's not just isolated, that it contains a circular orbit. Here is not exactly that it contains this neighborhood contains circular orbit, it's just not isolated. So another condition that it's was used in shape theory is the Mittag-Leffler condition. And this is Mittag-Leffler condition for first Vittori's check homology. Those type of conditions can be defined for any other invariants like higher homotopy homology or homotopy groups, but in the sense of either shape or Vittori's. And a compact set in some ANR satisfies the Mittag-Leffler condition if for every neighborhood there is a smaller one, such that for any additional homomorphism, this image, those two images are equal. So this is clearly not true for a solenoid because it wraps around more times. These images cannot be the same. They do change. If something is movable, then it does satisfy the Mittag-Leffler condition. So for instance, the Denjoy continua used by Paul do have the Mittag-Leffler condition. In fact, that Denjoy continua is the same shape as a bouquet of two circles. So the last remark, which I presume you cannot see, just says the
we can see now the problem here in Rio, in Niteroi, has been resolved.
Has been resolved. Great. Okay. So as looking at the continua again, let me see how much time I have. Okay, solenoids are not movable and do not satisfy the Mittag-Leffler condition. There is a very nice continuum called Case-Chamberlain continuum. There was another example of something that was not movable. And it's an inverse limit of bouquets of two circles. This was actually very useful to show that for cohomotopy groups that was used by Borsuk, there is an essential map onto a bouquet of two circles of this thing, but not onto a circle. So the A and B are the natural generators of S1 and the other S1, and you go around A, then B, then go back. Then with the other one, you do the same, except you go twice around, and don't go back. And one can show that this is not movable. The suspension, in the sense of spherical suspension, the union of two cones is movable. That was shown by Mardershitz. And does satisfy the Mittag-Leffler condition because the homology groups are trivial. Are not trivial, but very, I mean, they're very, very clear what they are. And the question related to dynamics, that there exists a minimal set A in a non-singular flow that has the same shape as the Case-Chamberlain continuum. So one thing to get this Mittag-Leffler condition is just kind of going back and forth the same way. And let me say a little bit about the Seifert conjecture. I'm not quite sure how much time I have. So
you have 10 minutes now.
You have 10 minutes. Okay, so we have Seifert conjecture and generalized Seifert conjecture. So Seifert conjecture in the original form says something only in dimension 3, that a flow on S3 always have a compact trajectory, and that was shown by Paul not to be true. But Wilson in 1966 really constructed a counterexample to Seifert conjecture in in higher dimensions. And there's generalized Seifert conjecture to higher dimension and modified Seifert conjecture, and then the flow possesses a minimal set of codimension 2. So in Wilson constructions, those are tori of dimension 2 lower. And counterexample to Seifert conjecture of Paul. Then Jenny Harrison improved that. Then Greg Kuperberg showed that it could be volume preserving. And Ginsburg and Victor Bassan-Gurel show that it could be a flow on R3 given by Hamiltonian. So he have a counterexample to the Hamiltonian Seifert conjecture in R3 or 4, depending how you look at it. And these are not C infinity, and these all are really modification of Paul's work, and the minimal sets um, should be movable. I said should because certainly somebody could change the construction a little bit and make something else with it. So the C infinity, actually real analytic, which was noticed by Bill Thurston, came in 94, 93, really 94. And also they somehow automatically all answer the modified cipher conjecture. Etienne Gilles and Anna Rachman and Steve Herder use that for the so-called generic construction, which uses polynomial of degree 2. In the paper of Greg and mine, we use a polynomial of degree 4 with C infinity, C infinity and real analytic construction, and the minimum set is clearly of dimension 2. So it was hard. Well, can it be in this particular construction of dimension 1, and we have PL minimal set of topological dimension 1, the same kind of construction. And I said something incorrectly because I said it was actually done by Greg, although it's in our joint paper with many other things. So Steve and Anna did a lot of work and really very impressive. They were looking at the counterexamples of this to the cipher conjecture that are C infinity, and they look at the minimal sets. The minimal sets are messy, are very complicated, but they show for this particular case with the insertions of given by polynomials, as mentioned too, that the minimal set is not in shape of a polyhedron, but satisfy the Mittag-Leffler condition. And as far as I know, whether they are movable or not, it's still an open question. And also, there are other constructions. You can make this minimal set very large, but kind of chopping off very little or very small, like in case of PL construction. But why the Mittag-Leffler is given, I feel that because of this going back and forth. So those constructions are based on this plug given by Wilson, that things just go back and forth to have the matching ends. That happens here also. And also that happens in Paul Schweitzer's example, that he has a plug, and if the trajectories go through that, go around and come back, and then you have this kind of symmetry, in some sense similar to the Keynes-Chambers example. And it's very important to those constructions to have the so-called match ends to assure that no additional circular orbits are formed. So I would like to thank everybody for listening, and happy birthday to Paul again. And that's my last slide. Thank you.
Thank you very much, Krystyna, for a fascinating lecture. Do we have any questions?
Why? I have to raise my hand.
Yes, go ahead.
Why do I don't understand when you were talking about the higher dimensional? You said it had codimension at least 2. When you were talking about a dimension bigger than 3.
The theorem of Wilson.
He lets you have yeah.
He takes a flow, there is non-singular. So for instance, on S5, S7, and so on, also on S3. And he modifies the flow using his plug. So here I call it differently, but it has the property of a plug. And he modifies such a way that basically every trajectory, every orbit has its alpha limit set and its omega limit sets inside some invariant set in the plug. That invariant set is a torus of dimension n minus 2. And on that torus, the flow is just irrational flow. So the minimal sets are tori of dimension n minus 2. Unfortunately, 3 minus 2 is 1, and there's a circle, right? So that's why it didn't work in dimension 3. But the codimension of, in Wilson's theorem, of the minimal sets is 2. So he stated, I believe, well, can we have examples, counterexamples to cipher conjunctions in higher dimensions, or dimension 3 was not known at the time, but so the codimension of the minimal sets is 1. So if the C-infinity construction, the minimal sets are dimension 2, and now we're talking about topological dimension, not Hausdorff or anything like that. You have codimension 1, and that answers the modified cipher conjecture as well.
But you put this conjecture only for odd dimensional sphere, but it's for any. I mean, bigger than 3.
The Wilson's theorem,
Yeah,
on any manifold of any dimension, and we
bigger than 3.
On which there is a non-singular flow, so it's not either non-compact, connected non-compact, or Euler characteristic 0. You have a non-singular flow. You can modify that. So the only minimal sets are tori of dimension n minus 2.
Yeah, I agree.
And his construction, he says C infinity, but it's really real analytic. If you want to make his construction volume preserving, then it just C infinity. But he just says C infinity. But that symmetry in a plug was first, as I believe, first used by him, but it was kind of rediscovered by Paul in a different way, and sort of by Borsuk as well. But the higher because of the C infinity constructions that have different minimal set, the higher dimensions are almost automatically covered.
I'm just wondering, Krystyna, whether it's possible to modify your construction to have just one minimal set.
It has just one minimal set.
Oh, I'm sorry.
The thing is,
I mean, you can put more minimal sets if you want more
Sure.
plugs, but the plug
Sure.
has one minimal set.
but one thing is that it's not isolated.
It's not isolated. The only question is it movable?
Yeah.
Is it movable?
Are there any other questions now? Well, again, let us thank Krystyna. And this afternoon is free. So we continue tomorrow morning at 10 a.m. in Rio time.
Okay. Thank you very much.
Good. Thank you, Krystyna.
Thank you.